Hello, my name is Mazdarani. I am a PhD student at Carleton University. The paper I'm going to present is on 2D ultrasound-guided visual servoing for in-plane needle tracking in robot-assisted percutaneous nephrolithotomy. This paper is from our research at the Biomechatronics lab at Carleton University under the supervision of Dr. Carlos Rossa. First of all, let's see what is PCNL. PCNL, which stands for percutaneous nephrolithotomy, is a minimally invasive surgical procedure used to remove large kidney stones that cannot be treated with other non-invasive methods. During this procedure, a small incision is made in the patient's back and a needle is inserted into the kidney to reach the stone. It has several advantages over more invasive methods, including faster healing, shorter hospital stays, and lower post-operative trauma. However, despite over 40 years of development, it is still a high-risk procedure. The most challenging task in PCNL is kidney access, and any small mistake in needle placement for reaching the stones may cause huge damage to the kidney or surrounding organs. Kidney access during PCNL may be performed using different imaging modalities, including fluoroscopy, which is the key standard in North America and Canada, ultrasound, which is being widely employed in Europe and Asia, or a combination of both. However, ultrasound has several advantages over fluoroscopy, such as its ability to detect radiolucent stones and improved visualization in a radiation-free setting, which is much safer for both patients and physicians. These advantages have caused a big push towards using the ultrasound instead of fluoroscopy in North America and Canada. But kidney access through ultrasound imaging is not a simple procedure at all. Ultrasound-guided kidney access can be performed through longitudinal or transverse images. In longitudinal imaging, the needle appears as a line in the ultrasound image. The surgeon must precisely coordinate the hand holding the ultrasound probe and the hand holding the needle to keep the needle shaft aligned with the imaging plane while steering the needle. In transverse imaging, the needle shaft is perpendicular to the imaging plane and therefore the needle shaft is not visible in the image. Both these methods need an extremely high level of proficiency and burden a huge workload on surgeons. Also, part of the kidney are shadowed by the ribs, which further complicates the procedure and may increase the chance of losing the needle visibility and accurately puncturing the kidney. These complications have created a steep learning curve with as few as 11% of urologists being able to achieve kidney access using ultrasound guidance. To alleviate the surgeon's workload and the complexity of ultrasound imaging procedure, several methods have been proposed. For example, one method is using a mechanical needle guide to keep the needle in the ultrasound imaging plane, but this is at the cost of limited dexterity. Another method is using augmented reality to help steer the needle toward the calyx. However, the most promising approach, especially in recent years, is robotic assistance, which has suggested several advantages over other methods. These advantages are including improved accuracy and precision, greater consistency, and reduced procedure duration. Robot-assisted needle tracking is among the best solutions to address the complexities of ultrasound imaging in PCNL. In this modality, a robotic arm that holds the ultrasound probe is used to track the needle as it is steered. However, there are some challenges. During manual needle steering, the position and orientation of the needle, which is steered by the surgeon, are not known beforehand, so real-time adjustments are required to ensure continuous visualization of the needle. A solution to these requirements can be found in visual servoing. Visual servoing is a technique to control the motion of a robot through visual information obtained from a camera or a sensor. Its primary benefit is its ability to accurately control the robot's pose relative to a target image or feature. Visual servoing is widely used in camera-based robotic applications. However, there are only a few works done on applying this method to ultrasound images. Although these works have shown the feasibility of using visual servoing with ultrasound images, they use 2D ultrasound only for scanning a static target. And also, needle tracking is only addressed through 3D ultrasound, which is more complex, has a lower frame rate, and may not be suitable for real-time needle steering. What we proposed in this paper is a new ultrasound-based visual servoing for longitudinal needle tracking using only 2D ultrasound images. It accounts for needle motion in 3 degrees of freedom, that is 2 in-plane translations and 1 in-plane rotation. Here is the paper outline. First, I'll explain the proposed visual servoing algorithm for in-plane needle tracking. Then I'll go through the experimental procedure, discuss the results, and suggest the complementary next steps. This is the block diagram of the proposed method that starts with defining a desired ultrasound image which represents the desired needle visibility. This image can be set at the beginning of each procedure when the needle becomes visible in the ultrasound image. From this point on, robotic assistants will track the needle. Our goal is to control the probe, which is attached to the robot end effector, to have similar images as the needle is moved. This means that we should minimize the error between these two images. So we extracted some features that can represent the needle pose in the ultrasound image. Then the visual servoing controller is employed to generate the control action, which is the robot velocity based on the error between the desired and actual image features and using the extracted interaction matrix. This velocity then goes to the robot manipulator with its internal controller to move the ultrasound probe. Through this method, we can track the needle as it moves toward the kidney. I'll explain all these sections in more detail in the following sections. As I explained, the first step in the algorithm is to define appropriate visual features that represent the needle pose in the ultrasound image. These features should be time variant and differentiable. This figure shows a sample longitudinal ultrasound image of the needle and a segmented image. This kind of segmentation is also used at this point in the block diagram. Here, the main features that can be associated with the needle are defined. That is, the needle shaft length in the image shown by L, the position of the needle tip in the image shown by X tip and Y tip, and the orientation of the needle shaft with respect to the ultrasound probe horizontal axis named theta. So we can define vector S including these 4 features, which is what we need at these points in the control loop. Now let's see how we can calculate these parameters. To calculate the presented features, we need image moments. An image moment of order I plus j is defined as an integral over the image surface, and in the case of digital images, like what we have here, it can be defined in this summation form. So the features presented in the figure can be defined in terms of moments of order up to 2 as follows. Here, parameter mu is called the centered moment and is defined as this. In the next step, we need to extract the interaction matrix. The main idea of visual servoing method is to find the relationship between the temporal variation of visual features and the speed of the ultrasound probe through this equation. Here, stat contains the time variation of image features, and V contains the ultrasound probe velocities in 3 degrees of freedom, that is 2 transitional velocities along X and Y and 1 angular velocity around Z axis. And LS is called the interaction matrix. To find the interaction matrix, we can use these relationships for each element in S. So the interaction matrix can be written as here. After extracting visual features and interaction metrics, the next step is to define the visual servoing controller. Here we use this control law, which determines the probe velocity based on the observed error between the desired and actual features and the extracted interaction matrix. By applying this velocity to the robotic arm that holds the ultrasound probe, we can track the needle as it is steered toward the kidney. And if we use a correct estimation of the interaction matrix at each sample, this closed-loop control system is shown to be locally asymptotically stable. In order to validate the proposed method, we use this experimental setup. Here, the ultrasound probe is attached to the end effector of a 6 degrees of freedom robot manipulator, Robot 1, and in order to have measurable and repeatable motions for the needle, another robotic arm is used to move the needle. However, in actual surgeries, needle steering is done by the surgeon. Also, we use the water tank instead of tissue, which allows for the free movement of the needle. In this setup, as Robot 2 moves the needle in the plane with 3 degrees of freedom, Robot 1 adjusts the position and orientation of the ultrasound probe to maintain the desired needle view. To validate this, we designed 4 test scenarios. In scenario 1, needle base only moves along its x-axis. In scenario 2, needle base follows a linear path in xy plane. In scenario 3, needle base only rotates around its z-axis. And in scenario 4, we have all 3 movements. Also, the test duration was 15 seconds with 50 millisecond sampling time for all scenarios. This figure shows the calculated feature error in each scenario. We can see that despite the needle displacement, we have less than 3 mm error in the needle tip position and less than 1.5 degree error in the shaft orientation with respect to the desired pose. These errors are sufficiently small to have a negligible effect on the ultrasound images, as can be seen in the next figure. Here we see ultrasound images of the needle at 3 time steps during the tracking procedure in scenario 4. As we can see, the needle pose has remained the same while it had motion in 3 degrees of freedom. This figure shows the measured displacement of the probe and the needle's base in scenario 1 and 2. And as we can see, the displacement error is very small in both cases. And here depicts the movements of the needle and the ultrasound probe in scenario 3 and 4. It shows how in these 2 scenarios, rotation in the needle base has changed the needle pose. These results suggest that the proposed control system can effectively track the needle during the in-plane motion. To summarize our achievements, I should say, to the best of our knowledge, this is the first visual servoing method for tracking a moving needle with 3 degrees of freedom using only 2D ultrasound images. And the results show that the algorithm can successfully track the needle as it is steered. Also, it is achieved without any prior knowledge about the needle trajectory. And of course, the computational time of the proposed algorithm for each sample is around 24 milliseconds, which makes it suitable for use in real-time clinical settings. However, this is the crucial first step toward automating kidney access during ultrasound-guided PCNL, and a lot of work is still needed to reach that goal. So our future work will focus on further improving the efficiency of the algorithm and redefining the interaction matrix to account for out-of-plane motion and to track the needle with higher accuracy. In addition, moving away from a water tank and conducting tests on a phantom or biological tissue can provide more realistic results. And of course, more precise image segmentation will result in a better estimation of the interaction matrix and higher precision. Finally, let's look at some statistics. The incidence of kidney stones is rising. About 12% of men and 6% of women will have a kidney stone at some point in their life. It is estimated that 30% of the surgical workload in urology is related to the treatment of renal and urethral stones. PCNL has a well-defined role in these treatments, and with the help of robotic technology, it will be accessible to more people around the world. Thank you. And if you'd like to be in contact, here is the link to my LinkedIn profile with my email and the Biomechatronics Lab website.